Hello everyone. Welcome back to your favorite maths channel on YouTube. Today I'm following up to a promise that I made you guys. That promise was if you are an avid viewer of my channel, I've got maybe two or three of those. So if you're one of them, in my previous video, I promised you guys that I would do a problem that involves using the theorem I taught you, which, if you don't know what I'm talking about, maybe click on my channel page and go and check that video out. But today, I am showing you guys that exact question. This one is it's from India. It was in their team selection test to determine who's going to make the IMO. It was question one, and I think it's roughly suitable for question one on the IMO. Enough talking. Let's do some maths. We're asked to determine all integer polynomials, which, by the way, forgot to mention, this is part two of my integer polynomial series. We're asked to determine all integer polynomials for which we have this divisibility. But let's just pull up the pen. This divisibility, I can't speak, which in other words becomes something like this, right? F of n divides this. Okay. Pretty simple statement, along with the extra condition that we have to have n is greater, like this only holds for all sufficiently big n. Simple statement, but not so simple a solution, and let's get straight into this. Something just fell down. For starters, you'll remember the theorem we talked about in episode 1, which you should totally check out. Episode 1, which was that d divides this difference when you have two inputs that differ by d and you take their difference, d divides that. So that was essentially the whole point of episode 1, which I showcased through a much easier question than this. So now I'm assuming that you're very happy with this fact. The next step is, guys, come on, work with me here. Come on. The next step is, oh, this is not good. This, right? So what I'm doing here is, in our previous simplified statement, we had d divides this difference. I'm replacing d with a multiple of d. So then that multiple of d divides this bigger difference over here, which means since d divides this multiple of d, d actually divides this bigger difference over here. So that's a cheeky spoiler. But on this slide, what I'm doing is I'm using this multiple of d as an intermediate step, and we're actually just getting rid of it. So all that matters is d divides this difference over here. Happy? We're happy. Let's go. Now, in my previous video, I taught you guys this theorem, which is that a number that is not divisible by a given prime. So in the video, I think I formulated it as x to the p minus 1 instead. That number has a remainder of 1 mod p. Now I'll just erase that because it looks a bit ugly. So setting x is 2, 2 to the p minus 1 has a remainder of 1 mod p. Which means that if we just raise both sides to some power, we get 2 to the k times p minus 1 is 1 to the k mod p. But 1 to the k mod p is nothing other than 1 mod p. So we, in essence, have 2 to the k times p minus 1 is 1 mod p. Multiplying both sides by 2 to the x, we get this relation over here. And now we can also take k as negative, and this relation still holds, because then we're just dividing both sides by 1, essentially, 1 mod p. So okay, those are the two ingredients. We're using the polynomial division thing in a slightly more advanced way here. And we're using Fermat's little theorem, again in a slightly more advanced way, as demonstrated over here. Now we're ready to tackle the question using those two little ingredients. So, as we've demonstrated by this, p dividing f of n means p divides f of n plus any multiple of p. So, if we pick p dividing f of n, then we can just say that p divides this weird thing over here that we were given in the question. And that would mean, since p also divides f of n plus kp, replacing n with n plus kp means that this is also divisible by p. Good so far. Now, notice that if we look at the remainder mod p, since if we're focusing on divisibility by p, the remainder is all that matters. If we're looking at the remainder, 2 to the n plus kp has the same remainder as 2 to the n plus k. The reason being, this beautiful slide over here, where 2 to the x equals, or is congruent to rather, 2 to the x minus k times p minus 1. So, okay, we subtract k times p minus 1 from the exponent, and we get that this is congruent to that mod p. We not only have this, but using the more advanced version of the polynomial divisibility rule, we get that since the difference is k times p minus 1, k times p minus 1 divides that difference, which means p minus 1 divides that difference. So, if we replace f of n plus kp with f of n plus k, we are subtracting a multiple of p minus 1. So, 2 to the f of n plus k is congruent to 2 to the f of n plus kp, mod p. And, I guess this is where we start to finish the problem. Now from here, notice that when we divide by p, the remainder is all that matters. So, replacing this with 2 to the n plus k and replacing this with 2 to the f of n plus k, we get that if we have p dividing f of n, meaning p divides this over here, p actually divides f of 2 to the n plus k minus 2 to the f of n plus k. That's actually pretty crazy. That's pretty crazy because now we can take k to be some negative number and choose p to be really big, since we can find infinitely many prime divisors of any polynomial. Choose p to be really big such that... Wait, hang on. Let's erase this a bit. Such that p is actually more than this value over here, where, remember, we have that extra annoying condition, right? We have that. Now we're actually at the stage where we can just go ahead and finish the problem. So, pulling out my pen here, I'm gonna go with green this time. Notice that when we have a divisibility, like some p divides something, all that matters is the remainder of that thing when you divide it by p. That's all that matters, right? So, since we know that f of 2 to the n plus k has the same remainder as f of 2 to the n plus kp when we divide by p, and this right over here, because I'm sick of saying numbers, has the same remainder as this right over here, we have that if p divides f of n, p divides this expression for all k. Or in other words, we can just replace m plus k, since remember k can be negative, with give it time, guys, give it time, with some number I. Obviously, I has to be more than or equal to m. Okay. Now, right, the game plan here is to choose a prime really large. And why do you want to do this? Well, essentially, our idea is to show that this thing is zero. So, if we make it really small and make the prime that divides it really, really big, we are forced to have this as zero. As if it's not zero, it will be some multiple like LP, which is always more than or equal to P. So we want this thing in the box to be less than P and have P dividing it, which will make it zero. And once we have it zero, we basically have f of x equals x. And I'm not going to fill in those details, that's something for you to do. But this is actually pretty easy. It's pretty easy because every integer polynomial happens to have an infinite number of prime factors. So, having an infinite number of prime factors, we can choose one that's really big. We can choose a prime factor that divides f of n, that's really big, and that's more than this for some I. And now we have that f of 2 to the I equals 2 to the f of I for all I. Since fixing an I, we can choose a p that's big enough, given the infinitely many prime factors thing. So yeah, that's how you approach this question. I think, as I said, it's now I'm a question one level, probably on the harder end. And I've left some details for you guys to fill in yourself. Hopefully that isn't too much of an issue. Let me know in the comments if you don't appreciate the style, but the style of, I'll let you do the calculations and fill in the gaps. That's kind of what I want to do for harder questions, since that's how you will improve better. If you're focusing and if you're not, just doing whatever as you're watching this video. Thank you guys, and I'll see you next time.